So one question was, a student was confused about clocks in the time dilation scenario. And the clocks are the following. So Alice has her clock. According to her, the beam just goes up and down. Bob is observing the same clock. He's observing Alice's clock. Okay, so Alice has her clock. Okay. But according to Bob, okay, watches Alice's clock. Okay. And he sees that. He also has his clock. Okay. He concludes that while his clock does 1.5 cycles, for example, it doesn't have to be 1.5. Her clock does only 1 cycle. Okay, so that's time dilation. I also emphasize that in order to conclude that, he has to time her clock with 2 of his clocks, right? So I noticed that he has his clock and not just 1, actually 2. Because she's moving. So he has to time the start of her cycle and the end of her cycle, which happen at different locations. And therefore, you have to have a clock at that location when the event happens, the start of the cycle, end of the cycle. Okay? So that was a question. There was also another question, a general question, is that why do we care about time dilation if the effect is so small? What's the big brouhaha? It sounds like we're studying something obscure. First of all, it's not obscure because as we'll see more and more, it's really a total new way to look at the connection between space and time, the arena on which everything happens. Okay, it's true that at small velocities, in comparison to speed of light, time seems to be unrelated in space, unrelated to space. But when you have large velocities involved, the connection between time and space become more pronounced. And you might say, well, why do we care? I'm not dealing with large velocities, okay? Or why do we care about such a tiny time dilation effect when gamma is 1 billionth larger than 1? And so my point is, when you say small, my question is small in comparison to what? Oftentimes when people say small, what they really mean is it's small in comparison to a human scale, okay? So here's a normal velocity, okay? This is not small, okay? Velocity of a snail is much smaller. Velocity of a bullet is much larger, and so you think of bullet as being fast and snail as being slow because you're comparing it with your own with your own time scale. However, human time scale is often irrelevant. So, for example, when it comes to electronics, electronics operates on much different time scale. It takes, I'm not sure exactly how long it takes to record 1 bit of information. Probably less than nanosecond, probably a picosecond. It's a good question. Another example is with GPS. Well, you have a signal, so you have a satellite, okay, satellite. And then the satellite is moving with some velocity, which is much less than speed of light. So gamma factor is still very, very close to 1. But now you have 2 time scales. you have a time scale that it takes to cross atmosphere. So this is about what, 100 kilometers, okay, with speed of light, okay. Time to cross the atmosphere. And this is not a relativistic effect. This is just dirt formula, distance, distance, rate, time. It's just time, distance over speed of light. Okay, 100 kilometers over speed of light. It's small in comparison to human time scale. It's whatever time scale it is, small, large, it is some time. And so we compare that, compare this with, you know, time dilation. It turns out that for GPS, these two time scales, you know, this time scale and this time scale, become comparable enough that if you don't include time dilation, your GPS will be really off. The time dilation really is included in a lot of technology. Then there are also questions about confusion between conservation and invariance. If you're still confused about that, I will post solutions to quiz 1. Email me. But I've gotten several emails about that. I've replied. I think students understand that. Students are beginning to understand why kinetic energy is not invariant. The value of kinetic energy is not invariant, but the fact of conservation is invariant. Same for momentum. And I want to emphasize that not all laws are conservation. Not all laws are about conservation. F equals ma has nothing to do with conservation directly. But nevertheless, F equals ma being invariant means that if you observe some process and you find that for that process, force was proportional to the acceleration, then you will conclude that force is proportional to acceleration in a different reference frame. That's invariance, okay? So in this case, there's no conservation even in the picture, okay? So those are a few comments that I have. Okay, so I guess this is enough for section 1. It's kind of a chit-chat portion of today's lecture. So the real lecture starts in the next section. Okay, see you in the next section.